All right, let's go ahead and get started. Good morning, everyone. Thank you very much for coming to the Q-Chem 6.2 release webinar. My name is Shannon Hauk. I'm a staff scientist at Q-Chem, and today I'm going to be talking a little bit about the research developments included in Q-Chem 6.2 specifically is kind of the focus of this webinar, but I'm also going to be, giving a brief overview of some of the developments in Q-Chem 6 generally. So just a sort of an overview of what I'll be talking about. I'll give a really brief introduction, and then I'll talk a little bit about some of the default changes that were made in 6.2 specifically, so that if you're running calculations and see that something's different, that should hopefully give you a little bit of a hint as to what to look at. I'm also going to be talking about some highlighted features in 6.2 for sort of the bulk of the talk, and then a really brief overview of some other features in the Q-Chem 6 generation. And then additionally, I'm going to talk very briefly about our cloud computing option, which should hopefully be released sometime before the end of the month, is what if everything goes according to plan. So just as a quick introduction, Q-Chem, as most of you are probably aware, is an ab initio computational chemistry software package used to model molecular systems. It is an open-teamware package, which means that it's a commercial software package, but we also have academic groups from across the globe who have access to our source code and are able to contribute new features, bug fixes. If they have a feature that they want to see implemented, they can implement that themselves, which is really cool. And the developers benefit from a robust, well-tested code base, where we try to make it as robust and well-tested as possible. And at Q-Chem, we have dedicated individuals in the office who are responsible for taking care of code maintenance, running regression tests, and running all the sample jobs, making sure that everything with the code is sort of ship-shape, and also taking care of some of the optimization that isn't necessarily new. Like it is research, but it's coding of established methods to keep our code base as up to date and fast and well optimized as possible. So between the 6.1.1 release back in December and the 6.2 release, which was in May, we had 91 code commits to trunk specifically, which is, if someone's developing a method, they make a bunch of commits to their own branch and then merge that branch into trunk. So that includes bug fixes, that includes features, things like that. So, and then from 26 unique developers, which again, that's only counting the merge to trunk specifically. And so on the right, you can kind of see the Q-Chem developer activity in terms of merges to our code base since 2006. Also, as a side note, I forgot to mention this at the beginning, but if anyone has questions, you can post them in the chat. And I will get around to those at the Q&A session at the end. So thank you. So to go over default changes a little bit, there were a pretty small number of default changes this time around. The first was for frequency jobs, reading geometry from previous jobs, all part of the same input file with the little @ symbols as a separator. We have set point group symmetry to false to avoid reorienting that molecule. In harmonic combiner jobs, we've also set no reorient to 1, which is true, and point group symmetry to 0, which is false. The biggest one that is probably going to affect the largest fraction of the customers out of all of these default changes is the geometry optimizations Hessian guess change. We have a new initial guess Hessian that's new and improved, that we have now made the default for all of the geometry optimizations that utilize our new geometry optimization package, which is libopt3. So if you see differences between Q-Chem 6.1.1 run and a 6.2 geometry optimization run, the initial Hessian may be part of that. So additionally, we have enabled RIK virtual orbital corrections by default for OCK-RIK frequency jobs, because in most cases, most customers will want this to be turned on by default, because it, provides more accurate results. So just a quick overview of some of our highlighted features. The first one that we have is natural Auger orbitals from the Krylov group at USC. So these basically, the Auger decay process is basically this process where you have a vacancy or hole in one of the core orbitals of an atom, and then an electron from the valence shell moves to fill that hole concurrently with an emission of an electron from the atom. And this sort of process is seen in things like, for example, X-ray spectroscopy. And you can see that in this diagram here on the left, which shows sort of a regular Auger decay, but there's other types as well. So specifically for this approach, because we've got a couple of different things that handle Auger spectroscopy in the 6.2 release, this natural Auger orbital feature or approach basically allows a molecular orbital representation of these types of systems. And these are implemented for CBS EOM methods. And it's, as I mentioned before, relevant to X-ray spectroscopy modeling. So you can see here a sample job, just so you sort of can orient yourself in terms of how to calculate these. We've got all of these keywords here. The ones in bold are specifically the ones I wanted to highlight. So you run this calculation. This is a sample job. You can find it in the manual. And you have this output that's generated. So you have the output file, and then there are also some molecular orbital file, or sorry, some Molden files that hold the NAOs, which you can then visualize in your favorite visualization package. Anything that handles Molden files should be able to handle those. So you can see I ran this here, and we have this core hole state, and then the valence decay states as well. So continuing with the whole Auger decay theme, we also have this contribution from Florian Matz and Thomas Yagao. They have basically enabled a partial Auger decay width. They a while ago implemented this core valence separation approach, where you can see all of the determinants necessary for describing Auger decay in a four-orbital system are kind of down here. You can sort of see them visualized there. The core valence separation approximation removes configurations associated with the decay, which is all of the blue ones. And then the problem is basically solved with the excluding all of the blue configurations from the space. Auger channel projectors are kind of similar to that, but the configurations that removed belong to individual decay channels. This is really helpful because it allows us to obtain partial decay widths via complex variable methods besides CCSD. You can look at more information in their paper down here. And by the way, all of these usually have a paper associated with them where the developers have talked about the implementation of it and talked about what sorts of problems they're using it for in their own research group. So you can, if you want more details on any of these, you can check out the paper listed in the bottom right-hand corner. So again, as a sample input job here, you see the EOM ACP keyword is kind of specifically what we want here. You'll want to pay attention to the basis set also. I've also put that in bold because you want to make sure you're using an approximate complex scaled basis set, and I should have highlighted the complex basis gen rather than basis. I apologize for that. But yeah, so this is the out version. There's an in version and an out version, depending on which of the determinants or which of the configurations you want to eliminate from the space. But when you generate this output file, it contains a list of all of the open decay channels and their partial widths for each core ionized state in this nice little table that you see here. So now this next one is from the Herbert group at OSU. they have implemented the DFT-CIS semi-empirical method, which is based on Grimm's earlier implementation, which they've cited in the paper that again is down there. The main motivation for this was to handle X-ray spectroscopy cases that weren't well handled by TD-DFT. So core to valence excitation energies are significantly underestimated when standard exchange correlation functionals are used in a lot of those types of simulations. And the problem with that, or well, obviously there's a problem with that, but the reason why that happens is because of systemic issues with TD-DFT's description of Rydberg and charge transfer excited states. They talk about it a little bit more in their paper, but that's sort of the gist of it. So the general idea here was to use CIS which handles the core valence excitations fairly well, but to use cone sham orbitals as the basis for that rather than the usual Hartree-Fock orbitals in order to add some dynamical correlation. So again, this is for sort of X-ray spectroscopy stuff. And there are two parameterizations available. One is Grimm's original one, which is B3LYP based. And then they also have a CAM B3LYP based one for X-ray spectroscopy specifically. And those parameterizations are of the semi-empirical part. So if you want to run one of these, again, this is in the manual. You can find it there. You can run it yourself. You have this input file with this DFT-CIS and DFT-CIS params. That second one allows you to determine what set of parameters you're using for it, or which parameterization you're using, sorry. And then you can see in this output file, it has the excitation energies the same way it normally does. And then it also has orbitals, which you can visualize in, I used IQML for this, but you can use anything that will visualize Q-Chem output files or FCheck files. So another one from the Herbert group is this dipole filtering for TTKS, which allows you to remove continuum artifacts in real-time simulations of time-dependent cone sham theory-based X-ray spectroscopy calculations. So this is, again, based on another implementation from another group, but basically, if you look at their paper, they compare the real-time implementation to the linear response formulation for this. And the transitions to the continuum, so sorry, a little bit of background. The linear response version has some approximations associated with it. For example, the core valence separation and the frozen orbital approximation that the real-time version does not have. The issue with using the real-time version is it's more expensive, first of all, and second of all, the linear response-based version, the real-time version is often contaminated by transitions to the continuum from low energy orbitals, which obscures key information. So the way of solving that is, as you see kind of on the left here, you can see that if you use the full set of dipoles, you get this spectrum with a lot of noise in it. And this is for, this is for their smaller system that they looked at. They looked at more chemically relevant examples in their actual paper. But you see that if you include only contributions from that one set of orbitals that you're actually interested in, you get a spectrum that looks a lot cleaner and removes a lot of the extra noise from those transitions. They found that from a practical standpoint, the linear response formulation was still more efficient, but because this dipole filtering technique avoids some of the approximations used in the linear response version, it can serve as a really useful benchmark if you're trying to validate your linear response-based results. So, yes. Now, we're hanging out in X-ray spectroscopy for a while. There's a lot of ones here, but this one is the non-orthogonal configuration interaction singles for the one center, two electron open shell case. So non-orthogonal configuration interaction, or no CIS provides orbital relaxation that regular CIS neglects by sort of ionizing core orbitals and then doing a maximum overlap method. It's been pure, it's size consistent, it maintains symmetry, that's nice. And this is an extension of the one center gnosis to 2-electron open shell singlets. So it captures sort of, high energy region of the spectrum, core to SOMO transition, shifts, spin splittings, things like that. And specifically the application that they looked at this for was pump probe time resolved near edge X-ray absorption spectra experiments. So I would be remiss not to mention the DFT performance improvements. We're shifting gears a little bit here that Xintian from Q-Chem has been working on. Basically we have, improvements to our parallel performance in DFT. And then also he's been working a lot on improving our density fitting and RI methods to provide additional speed up. So you can see, we'll talk about the RIJ, the Big Mem algorithm is one of the ones he's been focusing on for the RI part. But you can see even with just the parallel part here, let me see if I can find my cursor. Here we go. You can see our parallel scaling is already pretty nice for sort of this medium-sized system. And then you can also see that if you add RI with this RIJ Big Mem algorithm, you get this about 2 times, there's about a factor of 2 there in terms of speed up. And then the meta GGA has a really large XC component, and that's kind of why. So yeah, you can see that there. So that looks really nice. And then also, if this will proceed, we go. LogRIK is sort of if you're using a large basis set. So you can see over here as well, we're missing the 4-core point because it was very computationally expensive, but you can kind of get the gist of it. The aux basis J and aux basis K keywords are what you're going to want to use here, just requesting an RI basis or an auxiliary basis for doing this calculation, and this will automatically activate either RIJ or RIK. So, so you can see you get this very significant speed up, and it's been pretty well optimized for parallel scaling for large basis sets. So we're really excited about that. RI is still off by default for 6.2. So make sure you turn it on if it's appropriate for your system. For real-time NEO methods, so shifting gears again, nuclear electronic orbital methods basically allow you to incorporate nuclear quantum effects into your modeling of your system. This is all work out of the Hamschiffer group. It's, they've been doing a lot with it recently. There's a lot of features from their group, which we're all really excited about. So the real-time extension of this basically is similar to time-dependent Hartree-Fock and time-dependent DFT. You can get electronic and nuclear spectral features from the time-dependent dipole moment. So there's that as sort of the baseline that everyone's, the baseline that we're building off of here. Then the real-time nuclear electronic orbital Ehrenfest uses an Ehrenfest dynamics method to add dynamical interactions between other nuclei and the proton-electron subsystem. Yeah, that basically adds classical movement of the other nuclei into your simulation. And then taking it a step further, in terms of optimizing it and making it a little more computationally inexpensive, there's this Born-Oppenheimer real-time nuclear electronic orbital Ehrenfest model, which allows an order of magnitude larger time step which significantly speeds things up. And then there's also a QMMM option that allows simulations in complex environments with solvent and proteins and so on. This is a very nice extension of or it's not an extension of is probably the wrong word, but Matthew Chow out of this group did some neo-PCM stuff for implicit solvent. So this couples very nicely with that. So we also have, like I said, they've been working on a lot of new features recently. So we have faster Neo-SCF with the simultaneous dice optimization from Matthew Chow and Sharon Ham-Schiffer. The SCS RIMP2 and SOS orbital optimized MP2 for Neo methods from Jonathan Featheroff, also out of that same group. Which provides some improved accuracy over Neo MP2 at a competitive cost competitive accuracy with Neo CCSD at MP2 cost. Then we also have Neo multi-state DFT if you want to incorporate some sort of static correlation into your modeling of the system. And it's also worth mentioning, Matthew Chow gave a very nice webinar last year on the development of a lot of these methods. So if you want to learn more about these and sort of dig into the theory a little bit and want more details, definitely go check that out. So going through a couple of other notable Q-Chem 6 related features, there's this EOM CCSDT implementation from they actually just published this paper earlier this month, I think. So congratulations to them. We also have a VCD implementation, which was worked on by Kuan Yu in the Q-Chem office. We also have a new geometry optimizer that was rolled out with 6.0. So that's LibOPT3, which I mentioned earlier. It is a modernized geometry optimization library for Q-Chem. And so a lot of hard work has been put into that and sort of fleshing that out, developing it, optimizing it to make it faster, that sort of thing. We also have force decomposition analysis, which is a really nice extension of our existing energy decomposition analysis code or feature, I guess. So this allows decomposition of the force into individual components. Similar, again, like I said, to energy decomposition analysis. But it's really useful for figuring out what is contributing to a particular force or energy within a molecule. And then there's also the analytic VV10 Hessian, which is the first ever implementation in any code of the VV10 Hessian, or of the analytic VV10 Hessian. It offers probably around 5 times speed up over finite difference, and it's available for a whole slew of different functionals. And the parallel scaling is also quite good. It's about 80% efficiency out to 32 cores. And then also this optimized ghost chip implementation for quantum mechanochemistry, which is basically applying pressure to a molecule as part of your simulation. This is just a subset of the features. We also have like Neo with implicit solvent, like I mentioned earlier, EATD-DFT for core excitations, a whole slew of other new features. So definitely check out the changelog on our website for more info. And then also in the manual as well, there's a changelog associated with each of the new releases. Another sort of side note is maybe not the right word, but something that we've been excited about for a really long time and we're really looking forward to releasing is Q-Cloud, which is a cloud computing option for Q-Chem. So it allows you to run Q-Chem jobs on basically Amazon, AWS, EC2 infrastructure. We have a really nice command line interface for it, which Andrew Gilbert has worked really hard on setting up. The there are a lot of benefits to cloud computing, like, scaling up and down of resources. Basically, the way this works is you set up a little cluster, like a head node, and then the head node will launch jobs as you submit jobs to the cluster, um, and then scale resources up and down itself based on what you need at the time. So that reaches the sort of end of my discussion of new features and things like that. But many thanks to the Q-Chem developers. It definitely would not be possible to, you know, have a code base like Q-Chem without developers contributing to it, and people using it in their research and things like that. It's really exciting to see the sorts of work that they've been doing, and we're really excited to share it with you guys. So I also want to thank members of the Q-Chem team, uh, including Andrew and Kaushik and Kuan Yu and Sarah and Shintian, and thanks to all of you for your attention. And if anyone has any questions, please feel free to post them in the chat. Mm. Okay. Someone says they cannot find the section for DFT-CIS. I found it the other day. It is under, it's under the CIS section, I think, but let me grab the link for that real quick for you. Hang on. Someone is asking about new features in NMR shift calculations. We haven't had any of those in 6.2. If you're interested in any particular new features in NMR shift calculations, we are more than happy to submit a feature request on your behalf. Let me grab that manual link for you real quick, because I do remember that being a little tricky to find in the manual. And okay, yeah. We've got a question about there's a group that has found that libopt3 is quite a bit slower for large molecules. Any progress on that so far? I know that some members of our team are working on that. But I'm not sure. I can double check with them and see if there's any updates on that. But if you want to turn it off, you can always disable it by invoking the old library instead of the new one. But we definitely appreciate that feedback, because it's libopt3 is a new library, and we're constantly working on trying to improve it. Actually, let me do this real quick. Should be under uncorrelated wave function methods. Yeah, I think because there's a slash in there, it makes it hard to search in the manual. That's a thing I should make note of. Okay, so for those of you who are looking for the CIS section, I will go ahead and post that in the chat. And it's in section 7.2.2.4. It's buried in there a little bit, but it is a really cool method. So we're quite excited to have it. And to the person who asked that, I will also. Oh, okay, sorry. Kaushik has chimed in to say that NMR shifts are being implemented by Xiao and Martin's group, but they're not yet released. So we're working on the NMR shifts, but they're not in the released version of Q-Chem yet. Oh, it says chat is disabled. That is unusual. Thank you for letting me know. Let me. Okay. Is everyone, I guess, able to? Okay, everyone can post in the Q&A though, it looks like. So I don't know why chat is disabled. There we go. I've enabled it now, so everyone should be able to post in the chat. Thank you for letting me know. Okay, so the CIS section is now posted in chat, if assuming that everyone can still see that. Does anyone have any additional questions? All right, well, if no one else has anything, oh, okay, I will send that again. Here you go. I'll give everyone a second to grab that one real quick. And it's, if you're looking on the page, it's at the very, very bottom of the page. So, yay, excellent. I'm glad folks are looking forward to QCloud. Yeah, like I said, we're sorting out a couple of non-technical related things with that. So just, getting it set up as a product. But we're very excited to release that soon. So, well, I guess if no one else has any questions, thank you all very much for attending, and thank you very much for your attention. And if anyone has any questions that they think of after the webinar, you are welcome to post them on the forum. There will be a talk forum topic that specifically addresses questions from this webinar. So, and for those of you who are watching this on YouTube later, you are also welcome to post on the forum as well. Thanks everyone, and I hope you all have a wonderful Thursday. Bye.